Elette and Henry on zero-knowledge proofs on distributed data from fully linear PCP.
Great. So thanks for coming. I'm really happy to be here to tell you about some joint work with Dan, Elette, Niv, and Yuval. And I'm going to give the first piece of this talk on zero-knowledge proofs on distributed data, and then Alette's going to talk about some applications to multi-party computation and other things. So we've seen already zero-knowledge proofs. I'm not going to bore you to death with the definitions, but I just want to give you the picture so that I can give you the contrasting picture on the next slide. So think of a prover and a verifier, and think of a prover with a graph trying to convince a verifier who has the same graph that this graph is three-colorable. So of course, we want these protocols to satisfy natural notions of completeness and soundness and zero knowledge. And so in this talk, we're actually not going to be looking at this type of protocol. We're going to be looking at it's kind of a twist on the normal setting in which we have multiple verifiers. And now each verifier is only going to take as input a piece of the graph. So the prover has the entire graph and knows the three coloring, and is going to try to convince the verifiers that hold this graph in distributed fashion that the graph that they're holding together is three colorable. So we have different notions of completeness and soundness and zero knowledge now. So now completeness means that an honest prover should convince an honest pair of verifiers that the graph is three colorable. Soundness means that a cheating prover should rarely fool an honest pair of verifiers.
What do you mean, do you require that they all reject, or that?
So say they all reject, yeah. Yeah, and zero knowledge here means that if either one of the verifiers in the setting is cheating, is deviating from the protocol, the only thing that it learns is its input and the fact that the entire graph is three colorable. So in particular, verifier V1 shouldn't learn anything else about this graph G2 apart from the fact that it's sort of part of a three colorable graph.
Sorry, can they interact, the verifiers?
Yes. So I should have said the prover is going to interact with both of the verifiers, and the verifiers can interact with each other. And they can even share, say, common randomness.
So you're saying whatever the verifiers can learn by interacting alone, whatever they can learn there, that's essentially what they can learn with interacting with the prover. That's kind of the zero knowledge.
Yes, and the other verifiers.
Yeah.
Well, what the essence prevent them from exchanging information to appear as a single verifier?
So the question is, so your question is why can't these verifiers just simulate? Yeah, so you might lose this zero knowledge or privacy property. So if V1 sends its piece of the graph to the other verifier, this verifier now can simulate the sort of one verifier setting. But now V2 has learned this piece of the graph, which is essentially what we're trying to hide.
So how do you restrict the fact that there is these lines of communication between the verifier, looks like, that they will not exchange this information and appear as a single one?
So the honest verifier will not do this. So all I'm saying is
honest verifier and a bad verifier.
Yeah, so if one of the verifiers is dishonest, then that dishonest verifier doesn't learn anything else. Good.
Verifiers are dishonest, no guarantees?
As I've defined it here, if no verifier is dishonest, then you get no guarantees.
Why do you call it strong zero knowledge?
So yeah, so I guess the reason we call it strong zero knowledge is that the verifiers, each verifier neither verifier actually learns the graph itself. So it learns that it's sort of together they're holding a three colorable graph, but neither verifier actually knows what the graph is. So it's kind of stronger than the usual notion of zero knowledge. Any other questions about the setup? Yeah.
In distributed computing, when you say dishonest, the verifier being Byzantine. In Byzantine case, there is no meaning of he has part of the graph because it can lie about it and have anything. So what is the meaning of three colorable then?
So, right, so your question is, if this, say, verifier V2 is Byzantine, what does it mean for, so these notions of completeness and soundness still make sense. In the Byzantine case, it's just here the verifiers are going to be honest, right? So I've said that completeness means an honest prover convinces an honest pair of verifiers, and same for soundness. In the zero knowledge case, it doesn't actually matter whether V1 is Byzantine or not. All it's saying is that no matter how V1 deviates from the protocol, it can't learn anything beyond the input that I gave it, and the fact that the graph is three colorable.
Maybe it's asking what graph is the G2 is not defined.
I see. Yeah, but so I see. I mean, this G2 that you're saying, like the G2 that I gave as input to verifier V2. It doesn't have to read the input, but yeah.
But he can honestly emulate the protocol with respect to a different G2. Learn that G2 is too colorable.
Right, but that's not sort of violating the definition of zero knowledge that I've set up here.
So I guess, no, if you require that for the particular G2, that he only learns whether G1 plus G2 is 3 colorable for the particular G2 that you gave him, then there's a problem, because he can switch to a different G2.
So I guess maybe I'm not understanding your question clearly?
It wasn't my question.
Okay.
But, you can move on, but I'm just saying that if you insist that V2 gets a particular graph G2, and only learns whether G1 plus G2 is 3 colorable, then here's an attack that I'm proposing. V2 chooses a different graph G2 that he likes, and runs the protocol honestly about that.
Yeah.
And then the completeness, he will.
Yeah. No, the protocol will always reject in that case. So basically, so what this is saying is that for this particular G2, G1 plus G2, the particular graph that we're splitting up and giving to these verifiers, this is when zero knowledge holds. Yeah, good.
Will you give a definition, a formal definition?
No, I will not, but you can reverse engineer the formal definition from.
One time.
Yeah.
The prover knows how G1 and G2 are, G1 plus G2 is split among the verifiers?
Yes, the prover does know the splitting. Good.
You didn't answer my question. I thought you said that the verifier can be corrupted. No, you say the prover can be corrupted.
So for different properties, I'm requiring different things to hold. So if everybody's honest, then the verifiers accept. If the prover is cheating, then honest verifiers will reject a false proof. And here I'm saying that a cheating verifier doesn't learn anything about the graph that it's not supposed to learn.
This honest V was in this star, okay.
Yeah. So this is it's a twist on the regular setting.
There's no guarantee if the prover is cheating and one of the verifiers is cheating, for example.
That's right. Yeah. So actually we do talk about that extension in the paper because we're already confused enough. Then I'm gonna But you can definitely look at the setting in which majority of the verifiers are honest, but so there's lots of extensions that you can look at. Okay, but right. So you can also look at sort of multi-round protocols, public coin protocols, protocols with more than 2 verifiers. And to make things even more complicated, Elon's going to talk tomorrow about a different setting of zero knowledge or proofs with multiple verifiers. But I'm not going to go into that other notion of distributed verifier proof. Okay, so a particularly interesting setting for zero knowledge proofs on distributed data is when the input is split amongst multiple verifiers using secret sharing. So this comes up in MPC, like Alette's going to talk about in other applications. So you can think of the prover as having a vector x, and the verifiers each have additive shares of this vector. And they're trying to be convinced that these shares add up to a vector in a language. So if you just have seen this for the first time, it's not obvious why this should be useful at all. In particular, you might think that this is sort of a cooked up problem that I made just to solve. But it turns out there's a number of applications in cryptographic protocols and other things. So I'll just give one application to explain why this is interesting. So imagine a system in which you have multiple database servers, and each server holds, say, a linear secret sharing of a database. And we'd like a client to be able to increment one row of this database that's held at secret shared fashion across the servers without revealing to the servers which row the client is updating. So what the client can do is it can take its database update, so it wants to increment, say, the 3rd row of the database. It can split this update vector into 2 shares and send 1 share to each of the 2 servers. And the servers can add this update vector into their sort of shares of the database. Yeah? And this will have the effect of incrementing the secret shared database by 1. And we'd like to be guaranteed that even if the client cheats, even if the client sends garbage to the servers, that still the client should only be able to update 1 row of the database. So what this requires us to do is have the client sort of prove to the servers that these updates that it sent essentially add up to a low weight, a vector of weight 1. So this is a proof on distributed data. So this thing is actually used today in the Firefox browser for collecting telemetry data from the browser in a privacy-preserving way. This ships with the browser and is used by millions of people every day. And as far as I know, this is the world's largest deployment of PCP-based technology. So it's like, even though it seems kind of contrived, it actually has a number of applications like this. Yeah. Any questions so far? Okay, so there's a number of other applications that I'm not going to have time to talk about, to PIR writing and private messaging, private statistics, private ad targeting, and so on. And the languages that these systems need to work with are often very simple. So low weight vectors, low norm vectors, and so on. The zero-knowledge proofs on distributed data that were constructed implicitly in these prior systems all had communication costs that scaled linearly with the size of the vectors, so linear size proofs. And in this work, we show how to reduce the size of these, or the amount of communication, to either constant or logarithmic in the dimension of the vectors. And Alette's going to talk about MPC applications as well.
So the MPC, I happen to know that you can do multi-party computation that aside from something that you learn by the total output, you didn't learn anything about. So if I take multi-party computation and do zero knowledge on all the steps of the multi-party computation, why this not more essentially solve the problem?
This is a great question, so I'll let Elette answer this question, because this is because it's because otherwise we'll start talking about MPC and then we won't get to anything else. So okay, so what I'm going to show is that if you have a language L in question that's recognized by circuits of size C, then there's a public coin zero-knowledge proof on distributed data for this language that has a constant number of rounds and communication cost that grows linearly with the size of the circuit. So this generalizes some sort of special purpose schemes that were used or constructed implicitly in the literature, and we give some non-trivial extension to the setting that Nick asked about, where the prover and some of the verifiers collude. The second type of result we have is about kind of simple languages. So if your language is degree 2, has a degree 2 arithmetic circuit, then there's a proof on distributed data for this language that has logarithmically many rounds of communication and logarithmically much communication cost. So this is kind of an exponential savings when your language is simple. And this extends to kind of k-round protocols with slightly worse communication cost, and applies much more generally to kind of languages with structured circuits. So constant degree circuits and so on. So what I want to do now is explain how we construct these zero-knowledge proofs on distributed data by introducing this object called a fully linear PCP, or a fully linear IOP. And then I'll give you a taste of some of the constructions. So the way we construct these zero-knowledge proofs on distributed data is essentially in 2 steps. We first define this thing called a fully linear PCP, which is a twist on standard linear PCPs that we've seen earlier this week. And then we give, I guess, what you've all described as an information theoretic compiler from a fully linear PCP for a language into a zero-knowledge proof on distributed data for the language. So then we just need to construct new objects to feed into this compiler, and then we're done. So I know we've seen linear PCPs before. I'm just going to remind you again what they are so that I can show what the contrast is. So this is a notion that was defined by Yishai, Kushilevitz, and Ostrovsky in 2007, and has been super useful for a number of cryptographic constructions. So the idea is a linear PCP proof pi that attests to the fact that a vector x is in a language. This proof pi is just a vector. And the way you check this proof is the verifier reads the input. So this is the statement that the verifier is trying to check, the x that should be in the language. And it makes a constant number of linear queries to this proof. So a linear query is just a vector that's as long as the proof itself. And each query, the answer to each query is just the inner product of the query and the proof. So after, say, 3 of these queries, the linear PCP verifier should accept or reject. And there's sort of standard notions of completeness and soundness and zero knowledge that should hold in the setting. So a fully linear PCP is almost the same thing. The only difference is the verifier now no longer has explicit access to the statement x that is being proven. Instead, the verifier only gets implicit access to the statement x through the proof oracle. So what the verifier does is it gets to make a constant number of queries to the input and the proof jointly, and then has to decide whether to accept or reject. And still, we should get completeness and soundness and zero knowledge. Any questions about this model?
Constant, you're referring to the number of queries. This is the number of queues or the support of queue?
So I'm referring to the number of queries, not to the support.
The queue could have full support for
yes.
this.
Mm-hmm.
But x is always the right x, right? I mean, the PCP, even if it's following full statement, the x is right. It's
Yeah.
the same.
Mm-hmm.
Honest verifier or malicious verifier?
Honest verifier is your knowledge. Okay, so yeah, and we can also define sort of a notion of a fully linear interactive oracle proof that's just the interactive analog of a fully linear PCP. So what this is a prover sends you a proof, You send a challenge, the prover sends you a proof, you send a challenge, and back and forth for many rounds. And at the end, the verifier makes some number of linear queries to the input and all the proof oracles combined, and then has to accept or reject. So this actually naturally captures, I'm not going to go into the details, but naturally captures a number of existing proof protocols like GKR and CMT can be framed in this setting of a fully linear interactive oracle proof.
Sorry, can I ask you a question? So in the beginning, you can send a linear query to x and pi 1. Then can you ask a linear query to x, pi 1 and pi 2? You can assume it's all this generality kind of?
So I'm going to say this is a public coin protocol, and I'm going to defer all the queries to the very end. Yeah. Good. So now I'm going to show that if a language has a short, fully linear PCP, then it has a low communication zero-knowledge proof on distributed data. So this is kind of the compiler. And you'll see it's very, very straightforward. So the setting is we have these two verifiers. Each verifier has a piece of the input. So this verifier has a piece x1, this verifier has a piece x2, and the prover has both x1 and x2. And the prover is going to try to convince the verifiers that they're holding a piece of an x in the language. So the prover outputs a fully linear PCP that attests to the fact that x is in the language. It splits this proof into two shares using a secret sharing scheme, like a linear secret sharing scheme. And it sends one piece of the proof to each of the two verifiers. So now the verifiers have a piece of the input, they have a piece of the proof, and they want to simulate the process of asking linear queries to the input and the proof oracle. So what they do is they use common randomness between themselves to sample a set of linear PCP queries. And then what they can do is they can use the fact that we used a linear secret sharing scheme here to publish shares of the answer to this query that the proof oracle would have given. So this verifier takes the inner product of its query with its piece of the input and the proof, and this verifier does the same thing. And by adding up these two shares of the query answers, they can reconstruct the answer that the oracle would have given. Yeah?
In your earlier slide, the one with the example of a graph, you were considering the induced instance to be the sum of the graphs.
Mm-hmm.
That was also an example later on where you're considering the instance being shared additively. Is there any reason why now you're moving to the instance being shared, concatenatively?
Yeah. I've been going back and forth because they're essentially the same. You can move from one setting to the other without.
It doesn't seem like it makes a difference in the way you construct this.
No. Yeah. Mm-hmm. Good. Anything else? Cool. OK, so then after the verifiers do this for a constant number of times, so for each query, they can reconstruct the answers. Then they just run the fully linear PCP verifier, and they accept or reject. So the communication overall here is now proportional to the size of the linear PCP proof and a constant number of extra, say, field elements for figuring out what the query answers are. So once you construct this object, fully linear PCP or IOP, getting to a zero-knowledge proof on distributed data is very straightforward. I should say I just described kind of the non-interactive version here, but if you add interaction, the thing works basically the same.
Can you maybe say something about why this is like zero knowledge, or?
Yeah, so essentially, if the underlying fully linear PCP is honest verifier zero knowledge, then the only thing that say the malicious verifier learns is it gets to see these pieces of the answers to the queries. But this is exactly what it would have seen had it behaved honestly. So it's not learning anything by seeing the answers to the queries from the honest verifier, the shares of the answers to the queries from the honest verifier.
So, and do we have these zero knowledge PCPs that are linear?
Yeah, so I'll show them in 1 second. Yep.
They use the same string to sample to generate the query, right?
Yes.
So they sent the same query?
Yes. So they're not actually sending the query anywhere. They're just simulating the process of asking this query to the input proof oracle. Yeah, so they use, say, a coin flipping protocol to agree on the randomness they'll use, and then they. Mm-hmm. Yeah.
I can understand if pi 1 is supposedly random, then from the sum, from the inner product, you don't learn anything about x1. But pi 1 is not necessarily completely random string. So why there is a zero knowledge here?
Good way.
Why you don't learn about x? Why x2 doesn't learn about x1?
Yeah, so when I said, I kind of hid this under the rug when I was saying the prover splits this proof into two pieces using a secret sharing scheme. And you can think of the prover as sending a random string to the first verifier and a random string minus the original proof to the second verifier. So each of these proofs independently hides, information theoretically hides the true proof. I was worried you were going to ask about MPC, and then no problem. Okay, good. So so now let me explain how you construct these fully linear proof systems. So maybe the first thing to see is it's either good news or bad news, but actually many existing linear PCPs that people use in practice are already fully linear. So if you look at the original construction from the IEKO paper or GGPR style linear PCPs, they already only make sort of linear access to, the verifier only makes linear access to the input. So this is great. And these things also satisfy honest verifier zero knowledge. Is linear PCPs. The downside is that the proofs are large. So for a circuit of size C, the proof size is C, or maybe 2C, something like this. What we show is you can actually get shorter proofs for languages with structure. And this is important in our application because the efficiency of the zero knowledge proof on distributed data, essentially the communication grows with the size of the proof. So the shorter the proof, the more efficient protocol we get. And yeah?
Linear PCP is the right way to go for this centralized. I mean, do you have like deduction to the other direction as well?
I haven't thought about it, and I think there could be certainly other approaches. I actually think maybe based on MPC or other things, but yeah, it's a good question. Yeah?
I lost some state on this. Do we have lower bounds in the length of either linear PCPs, or probably not with rounds, because now we just started only studying what happened with number of rounds. Like, in other words, should I only expect shorter PCPs for structured languages, or do we have a hope of maybe even for all languages with enough round complexity to get something non-trivial?
Yeah, good question. So the question is, should we expect shorter linear PCPs for arbitrary languages, or is this linear circuit size inherent? So for standard linear PCPs, I don't think we know, and I think you'd have to make some complexity theory. You'd need to make some assumption that this that proves such a thing. At least I think. For fully linear PCPs, it's actually pretty straightforward to prove via communication complexity a lower bound that says essentially, say if the proof size is square root, then the communication needs to be square root between the verifiers, and I think you can trade one for the other. So if you have a constant number of queries, then this is the best proof size you're going to be able to get in a fully linear setting. If the verifier is able to read the entire input, then it's less clear, because now there's kind of no information hidden from the verifier, and yeah, it's not clear anymore. Cool. Okay, and so there's a number of ideas that sort of use ideas similar to the ones that I'm going to present. Yeah, so what I want to do in the time I have left is to give you some intuition for how we construct these fully linear PCPs. So again, the first result I wanted to mention is that if your language has a circuit of size C, then you get a zero knowledge proof on distributed data with communication costs rough order C. And because of this compiler I just showed, from the existence of fully linear PCPs with linear size proofs, which you can get from this GGPR result, this theorem follows. But what I want to do is sketch the construction of a fully linear PCP with a linear size proof. Both, if you've never seen a fully linear PCP before, it'll give you some intuition for how we construct them. And second, if you've seen the GGPR linear PCP, I think I'm going to present it in a slightly different way that's amenable to generalizations that we'll need for the next result. So, yeah?
So is the theorem statement cryptographic? Are you compiling the fully linear PCP with...
So it's not cryptographic in the sense that this is unconditional. Is that what you're asking?
I mean, if you do the GGPR, if you actually want to send something, isn't it like exponentially long?
No, no. These proofs are not. These proofs are linear in the circuit size. So if you're looking at a polynomial size circuit, the proof is
Okay.
yeah. And you'll see, I guess, when I show what the proof is, it'll explain why. Okay, so let me explain how these things work. So say we have the following language. So I want to test that some field element x is in the set 0, 1, 2 in a big field. So this is a circuit that computes this thing that's 0 if and only if this is true. And so what the fully linear PCP is going to be is the coefficients of 3 polynomials. I'll call them f, g, and h, and each has degree roughly the circuit size. So I'll explain what the proof is, and then I'll explain how we check the proof with a constant number of linear queries. So the proof is going to be these 3 polynomials, and I'll define them like this. So I'll let this polynomial f essentially encode the values. The proofer is going to take this value x, and it's going to run it through the circuit, and it's going to get the values of all the internal wires in the circuit. And then f of 1 is going to be the value on the left wire of the first multiplication gate, and f of 2 is going to be the value on the second wire, or the left wire on the second multiplication gate. So f sort of captures all the values on the left input wires, and g captures all the values on the right input wires. And then h is just going to be f times g. There's only 3 polynomials constitute the proof. And if you think about it for a second, you'll see that since h is f times g, h of 1 and h of 2 encode the values on the output wires of the multiplication gates in the circuit. Anyone has a question? All right. So this proof now has size linear in the size of the circuit. So now to check the proof, yeah?
The degrees of f and g is the size of a circuit, but the degree of a?
Twice that, roughly. Yeah. Yeah, I'm taking the lowest degree polynomial. Yeah. So So now to verify this proof, the prover gives me oracle access to f hat, g hat, and h hat that are supposed to satisfy these relations. And now I need to check that these relations hold with a few linear queries. So essentially, like most of these proof systems, you kind of want to check that the proof is consistent with the inputs. So here I want to check that, say, f hat of 1 is equal to the x that I'm expecting, and g hat of 1 is equal to, say, x minus 1. So I want to check all the inputs. Then I want to check the output. So I want to check that h of 2 is 0. And then I need to check the internal wires in the circuit. So I need to check that the addition gates are computed correctly, these sort of copies are computed correctly. And finally, I need to check the multiplications. So it turns out all of these affine checks can be done with one linear query. I can take essentially the linear combination of a random linear combination of these affine checks. With one linear query, I can check all of those things. And then evaluating f and g and h at a random point can be done with 3 linear queries together. So if you put all of these checks together, it just requires 4 linear queries no matter how big your circuit is. And the soundness is like circuit size over field size. And as an optimization, you can actually get rid of f and g in the proof also. So this is a very, very simple and concretely efficient construction, which is why you can use it in practice. OK, so for a circuit with, say, m multiplication gates, yeah? Good. So I didn't explain how that works, but it's very, very simple. All you do is you set the constant term, say f of 0, g of 0, f of 0, and g of 0 to be random values. And that's enough. Yeah. Great question. So the downside is that this proof size grows with the size of the circuit. And essentially this construction I showed matches the complexity of this GGPR style linear PCP. But even so, the consequence is nice. We get a sort of a linear communication zero-knowledge proof on distributed data for arbitrary circuits. Getting to smaller circuits is actually shorter proofs for structured circuits. Yeah?
You mentioned that this linear size construction generalizes prior specialized linear size approaches to this problem. There is also compete in terms of efficiency with those approaches, or those specialized approaches are still better anyways.
Actually, I think this is slightly simpler. It's not a huge difference, but basically the prior approaches didn't cook zero knowledge into the fully linear PCP, so you had to add it in whatever external protocol that you were using, which is slightly less clean. Right. So what you can do is if your circuit has structures, so say it has a repeated gadget that's used in a bunch of places, call it G gate, then the proof size actually scales. If you just generalize the construction I just showed, the proof size ends up looking like the number of these G gates times the degree of the G gate. So if your circuit has a repeated subcircuit in it many times, and you're lucky and that repeated subcircuit has low degree, then you get a short proof. In particular, could be sublinear in the circuit size. So it's just one kind of toy example you can think about a circuit for testing whether a vector has a particular L2 norm. And this has a lot of structure, and so you can get, say, a square root size proof. And as a result, you get a square root size or square root communication protocol. Okay, so the last thing I want to mention is how we can get even shorter proofs for structured languages. The idea here is we use this new fully linear PCP construction, but we kind of use interaction to recursively outsource the verifier's work to the prover. So what it looks like is the prover sends you a fully linear PCP, but then instead of checking it yourself, you send your random coins to the prover and you say, prove to me that I would have accepted this proof had I checked it. And then the prover sends you a proof, and you kind of recurse all the way down until there's a constant size thing that you can check yourself. So if your circuit has a lot of structure, then it's amenable to this kind of recursion, and it turns out that low-degree circuits do have this structure. Okay, so that's what I wanted to say. So this has been about zero-knowledge proofs on distributed data in the setting of one prover and multiple verifiers. The proofs that you get are information theoretic and super lightweight. And I hope that this idea of a fully linear proof system made sense. I think there's a bunch of work to do in understanding the relationships between these ideas and others. I've talked to Justin a little bit about this. One thing I wanted to mention is, I guess we've been thinking a little bit about kind of best of both worlds proof systems in which you make linear access to the input, but then point access to the proof. And it would be interesting to kind of see how easy or hard it is to construct those things. And I guess Elette will talk about applications to MPC now. Thanks.
You want questions now, or?
I'm happy to defer them until the end. But
The second part of the talk will be given by Elette.
I'm like Madonna, I don't need to. Okay, great. So excellent. So this is indeed the follow-up to Henry's talk, and I'm going to be shifting gears a little bit. So Henry was talking about a bit about this notion as a definition and how to construct it, and I'm going to be talking purely about how to use it. Okay. So let me start you off with a little bit of a quick refresher. Hopefully you haven't forgotten this yet. But just to remind you, so here I'm going to be talking about really just sort of using as a black box this notion of a fully linear PCP. Okay, and this is indeed where the verifier only has linear query access to x and pi together. If the careful among you may have noticed that in Henry's x was small and pi was relatively big, I'm going to be, oh, this looks precarious, doesn't it? Do this again. So here, not by accident, I'm going to be kind of thinking about a setting where pi is small, smaller in particular than the input length, the statement, sorry. Okay, so as you saw, this is interesting not just for things like NP, but even for simple languages and relations. Okay, so for example, even if x, the relation I want to show, is something like a degree 2 relations hold here, this is still a very non-trivial and powerful object. And in fact, so from Henry's talk, we have constructions for certain simple classes of relations. So for example, things like if you have repeated copies of exactly the same subcircuit, you get some savings. And the one that I'm really going to be using today, right now, is just for degree 2 relations of the statement. Okay, so again, not even language here, there's no witness, just some statement, potentially big. and we want to argue that it satisfies some degree 2 relations. Okay? So I'm going to assume now that we have a construction of such a thing that satisfies this strong zero knowledge. Again, this is kind of a non-standard term, but by strong zero knowledge, I mean that the interaction, these answers that the verifiers receive, don't reveal anything about, okay, so witness, if you had a witness, but in particular about X, the statement itself. Okay, and that the proof size, here pi, is going to be sublinear in the size of X. Okay, so this is, this topic is, this part of the talk is going to be about applications. And really kind of the crux that I want to convey here, one of the reasons why is this notion potentially interesting? Because it allows you to prove things in settings in kind of a generic way, where potentially the verifiers only actually have linear access. They don't have full access to the input, but maybe they do somehow in one way or the other, they're able to learn linear functions of this thing. Okay, for example, suppose that, and then indeed this is also copied from Henry's slides. So for example, suppose it's the case that neither verifier actually even knows the statement itself, X, but only has pieces of it. Or for example, you can think about secret shares, additive secret shares. Okay? So in this setting, this sort of allows you to directly translate this abstraction, this fully linear PCP, into proofs in this kind of distributed statement setting. Okay, so for example, I could either, the prover can just kind of send pi over. If you want to preserve zero knowledge, you can send just some sort of additive secret sharing of the proof pi. And now these verifiers can start interacting and running already. Okay, and it's, so this is an example of distributed data. Secret shared, if it's some sort of linear secret sharing scheme, then verifiers again can do these linear pieces on their separately and to be combined. Also, I just want to mention, I'm not going to use this anymore, but for example, if the statement is hidden, maybe it's encrypted or something like that, or committed to, but you do have some sort of linear homomorphism involved. Okay. And just to kind of re-mention, this was exactly one of the slides that Henry said. So I think that this setting is something that could be very interesting in general. I mean, for example, ideally you could think about something, maybe I want to prove something about my health and my monetary status or something. So for example, one of the verifiers might be a bank, one might be a hospital. They don't have, and nobody has the full combined statement of this, but everybody has pieces. Okay, and another example of this, as Henry mentioned, is actually used in Firefox. Okay, so I'm not, wow, when did I start? Okay, good. Well, you don't talk too fast, but, okay, so the rest of the talk, I'm going to be focusing on an application of secure computation. So here, this is some secure multi-party computation. I'm going to refer to this on and off as MPC, if you see that on the slides. Okay, this is the setting, as you likely know, where there's a collection of parties, each with some secret inputs and some kind of global function f. The goal is to learn the output of f on the secret inputs, but without revealing anything else about the inputs. Okay, and this should hold even if some fraction, say, of the parties is corrupted. Okay, so beautiful results, feasibility results back in the 80s. We know that this is possible for any efficiently computable f. We can do this, assuming either honest majority or computational assumptions. For this talk, I'm only going to be talking about the honest majority case. So here you can hope to actually get information theoretic security, but I'm going to be, because I'm going to be kind of interested in practicality. People who know me might question that a little bit, but I'm interested in constants and things like this, so we'll toss in, for example, PRGs. Okay, so the question, what about the communication complexity? Okay, so I want to run some secure computation for function f. And say, so to be a bit more concrete here, suppose that f is represented with some circuit, maybe arithmetic over some ring or Boolean, okay? And how much communication do we have to spend to do this securely? So for example, if I didn't care about security, we could just have, say, size of inputs plus size of outputs. Okay, so the answer to this question depends a lot on who you talk to. So for example, in the theory land, the communication asymptotically is essentially size of inputs plus size of outputs, okay, with probably security parameter and so forth. But this is this is not the sort of protocol in general that. So there's a lot of overhead. So for example, this is using fully homomorphic encryption or homomorphic secret sharing or some sort of relatively heavy cryptographic tools. Okay, so now once you turn to the more practitioner line of research within secure computation, in practice, the answer to this question in many settings is the following. So say that I have a circuit representation of this thing, then the communication is going to be some relatively small constant times the size of the circuit. Most of the time, it's just the multiplication gates, okay? And this is a long line of work trying to get this constant down. Just to kind of be a little bit more concrete about what do I mean, what am I allowing myself here? For example, what separates these two? Let's say, for example, I'm allowed black box access to a pseudorandom generator, but that's really it. Okay, so efficiently, that's not so bad. Okay, and so zooming in a little bit more here about this complexity, even dating back to the original works in MPC, the structure of how to build secure protocols almost always satisfies the following framework. Okay, you start by building some sort of relatively weaker security protocol against passive or semi-honest security. So here it's assumed that the adversary does follow the protocol, but he's trying to learn more than he should about the information. And then you compile up to get kind of the standard security, where here you also consider guys who are trying to ruin your life by sending bad messages. Okay, so taking a little bit more of a look in computation here, communication here. In some sense, we're pretty happy with the state of affairs down here in the semi-honest case. Okay, we have like the lightweight protocols. Alpha is 1, which is pretty good. And in some sense, I mean, this is an interesting question for debate about whether this is inherent or anything like that. But as far as really we know how to do now, this is kind of the best. Okay, and the question that's, I would say, less well understood is exactly this red arrow here, how to get, go from semi-honest to full active security. Okay. So a little bit of an aside, this is all, you can't really tell. This is minorly grayed out here. I'm probably not going to have much time, but I want to give you a little bit of a flavor of some existing approaches for this red arrow here. So the original approach, going back to GMW, Goldreich, Micali, and Vigdorson, is roughly that the parties, so suppose, what I mean by this red arrow, suppose that you have a semi-honest secure protocol. How can you now somehow enforce the parties to act in a semi-honest way? And what they did in this thing is, so first they everybody had to commit to their inputs, you run some sort of coin tossing, but then in the protocol, in every single message that you send, you would also accompany this with some sort of zero knowledge proof that this was the message you were supposed to send. Okay, this is actually a beautiful compiler. I'm jumping the gun a little bit. What I want to say, so there's two maybe limitations on this compiler. One is, unfortunately, the overhead is pretty high, like the size of these zero knowledge proofs and so forth. And the second is that in some settings, so here, in order for this to work even, it has to be the case that the people, everybody, knew what the statement was. So I'm proving in zero knowledge that I'm performing the next step, but it has to be that people know, sort of have the full, for example, even just the message that I'm sending, everybody would need to be able to see this. Okay, so this works if you have a protocol over, say, a broadcast channel, but if you have something with point-to-point channels, then this approach, it's not really clear how to proceed. So maybe, fast forwarding about 20 minutes or so, what we provide with these fully linear PCPs can be viewed as a form of a GMW compiler, but over a distributed setting. Okay? Okay, great. So this is back to the previous slide where we were. And this is the state of affairs in terms of our alphas here, this constant multiplicative factor. Okay, so the main result that we give in terms of this MPC part of applications is a new compiler, a new arrow going from passive to active security. This works not for any protocol, but for protocols that satisfy a particular natural structure, okay, natural maybe in quotes, And I'll talk about what this is here. But the benefit is that going from passive to active in our compiler has only sublinear additive communication. Okay, so here say you have a very big circuit, whereas existing approaches required you to now at least communicate another copy of the circuit or more. Now this is, if you have some sort of alpha elements required to be communicated per party per gate in the bottom, now you'll get amortized over the circuit size, you'll get the same alpha.
The structure you need on the protocol, but the circuit is arbitrary.
Correct. Yeah, in fact, so sort of what we're going to leverage is the repeated structure of just the fact that you have a bunch of kind of multiplications, essentially. Okay, so this is a generic compiler. Of course, it depends a little bit on what this natural is, how interesting this compiler really is. So let's see, applying this compiler to existing protocols, let me tell you about some of the things that we can achieve. Okay, so one particular setting that's quite motivated, and this is what I'm going to focus most of my time about today, is the setting with 3 parties, 1 corruption. Okay, again, remember I'm saying everything that I'm talking about is going to be honest majority. And the reason why people have really, this is one area, I mean, this is not a complete list of citations here. One of the reasons that people really care about this is that in some sense it's kind of the minimal, not really, but maybe the easiest setting of performing secure computation. Okay, so clearly kind of you want fewer parties makes things cheaper, but going from 2 to 3, if you go to 3 parties with 1 corruption, this honest majority can really help you out in terms of efficiency. Okay, so comparison, and the existing results in terms of what is, and again, all of this is kind of going back to what is the alpha that you can get, this constant multiplicative overhead, depends a bit on what your ring is that your circuit is over. Okay, so for example, if I'm over a large field, it was known how to get alpha equals 2. On the other hand, so this really leveraged the fact that you get something like 1 over field size soundness error. So if the field is very, very large, this can help you out. For the Boolean case, if I start with the Boolean circuit, the best that we knew how to do was alpha equals 7. Okay, and this is, after a lot of authors, a lot of papers, and, a lot of these things in some sense require a lot more work and clever ideas than what we do, which maybe is a good thing, a bad thing. In any case, using this compiler, we can now get this alpha down to 1. So really it is just additive sublinear overhead from the semi-honest with this lightweight and alpha equals 1. Okay, now another mention here. So this is not only alpha equals 1, but this actually works. So we can run this even with small fields, and so not quite general rings, but anything of the form Zn for any n that you like. And kind of, so I'll discuss this a little bit. I'll touch on it a little bit later of how can we do that. But really, in the one sentence broad stroke is that because we have this sublinear communication that we have to add, we can really be very sloppy in terms of things like, embedding or multiplicative constant overhead factor of that thing because it's still sublinear. Okay, whereas in these ones, people really had to be very careful of making sure that there was no sort of waste anyway. Okay, so this is the core that I'm going to talk about. We can extend this. As you'll see at the very end, it takes quite a bit more work. But what we can achieve is, so for any constant number of parties with honest majority, anything honest majority. So beforehand, over a large field, the best was, say, 3, alpha equals 3. Once you go to Boolean, the situation became much more questionable, something around 40. And again, so here, we're not at 1. You'd ideally want something like this. But this is, again, matching the best, I believe, for the best semi-honest. Okay, so this scales if you plug in t equals 1, n equals 3, that matches this. And it gets slightly worse as n gets bigger, but it's still bounded by 1.5.
Okay. This is kind of highlighting the communication. What about computational complexity?
Good. So the computational complexity is still quite reasonable. It's higher, but it's still, certainly in any sort of setting, if you're bandwidth limited or like even reasonable bandwidth limited, there's some sort of trade-off.
understand. Where does n show up?
The capital N here, or?
Little n?
Oh, little n.
So it's not in the alpha, because you're writing an explicit expression.
So just a second. So remember that alpha is a number of elements per party per gate. Is that?
Where do you need to assume that n is constant?
Ah, good. So here, this is in order to, I'm not going to be able to go into it. So this is compiling, the base protocol is Damgaard-Nielsen protocol. And there, in order to get even the semi-honest version down to 1.5, you have to do some tricks with, like a bunch of the secret shares you send out are actually generated by pseudorandom generator. And then in order to do that with low communication, then it blows up kind of exponentially in the number of parties. I'd be happy to work it out later on. Yeah, so here it's the computation starts growing poorly with n. And in fact, actually, that's probably a good thing to point out. So here, because of that, there's also some sort of sweet spot that, like, if n gets pretty big, I would not recommend this as a practical protocol because of the computation. Okay. So for the rest of the talk, which I'm clearly not going to be able to do, okay, so I had kind of ideally decided to go through and describe to you a passive secure protocol, and then show how we build on top of that. Maybe if the chairs aren't paying attention, I'll go for it. Okay. Okay, so it is feasible. Okay, so I'm going to do this really quickly. If you don't follow, I apologize, but I probably should keep going, and I'm happy to go through it in more detail afterward for anyone who's interested. Okay, so let me start with one of the passive secure protocols that fits this sort of natural property, which I'll kind of semi-define, that allows us to build on top of it. Okay, and this is going to be based on, for those who know, it's like a replicated secret sharing protocol. Okay, so we've got our 3 parties. The first step is each party will secret share their inputs. How will they secret share their inputs? Well, this is not just going to be additive secret sharing. So this is kind of the first thing. Say that I have my secret A. I'll first generate additive shares of it, but I'm going to give these shares not just to one person each, but each share will be held by 2 people. Okay, so here the shares are, say, A1, A2, A3 that add to A, but everybody has 2 of the 3 shares. Okay. Next, in the same sort of fashion, we'll generate sets of shares of this form, but of 0. Okay. So in the same sort of way. Now, suppose that this is the gate that we want to evaluate. We're going to take these shares that we have and gate by gate do some sort of step. Okay, so note that this is a linear secret sharing scheme. So any sort of addition gate we can just do locally on the individual shares. And in regard to multiplication, so note here that so what do we really need? Say I want to multiply, I have 2 wires, one is supposed to hold A, one is supposed to hold B. We have these shares of these values. To generate shares of the product, or even to sort of reconstruct the product, you need all of the 3 squared cross terms. Okay? But we're in good shape because each person, or rather, so each pair of these terms is actually held already by some party. Okay, so let me draw this out. So say these are the 3 parties. Remember, for example, I have these, you have these, the third guy has these. So what each of us is going to be able to do is to generate 3 of the 9 cross terms locally. Okay, these actually now satisfy the property that these are additive shares of the product. Okay, they're not random additive shares, so we'll use the shares of 0 to mask these, to make them fresh additive shares. So this now I'm representing by these values. And now the only thing you have to do is we have to get back to this replicated state. But this really just requires that I send my share to one other guy, you send your share to somebody else, and so forth. Okay, so this is kind of one communication of an element per gate, per party.
The alpha equals 1.
Yes. Yes. Okay, and then finally, so once we reach the output gate, we all have this kind of share of the output. All you have to do is everybody sort of sends each other their shares, and we can reconstruct. Okay, so a couple different things. Let's start by taking a look at the communication here. So if you take the protocol as it is, and you actually do these shares and everything with random values, this is actually even information theoretically secure. Okay, but we want to try to drop the communication down, and I'm allowing black box access to a pseudorandom generator. So this allows you to do various tricks. For example, now these things, these sets, like lots of secret shares of 0. Well, what are these things? They're sort of a bunch of random values where certain people have copies of the same random values. You can compress these random values, say with a PRD or a PRF. So amortized, this is actually even going to go away. Okay? And what you're left with, so this is also kind of, for example, some of these other things are under the rug using some pseudorandomness in order to compress things down. For example, it can always be the case that 2 of the shares are random and the third one just has to kind of add up to the right thing. This allows you to save on communication. Okay, so ultimately this gives you 1 element per party per gate. I guess you also have the 1 per input and 1 per output. Okay, so some observations about this protocol. Okay, let's start getting this in shape here. The first thing is this secret share of the inputs. So remember, what was this? Everybody had to take their input, share it in these pieces, and send it out in this form. Given correct values here, this already implicitly defines an input for the adversary. So what he's given, why? Because if these 2 guys are honest, we have a copy of A1, we have a copy of A2, and we have a copy of A3. We can extract the input. Okay, so what he sends, it commits him to an input. Another observation, above this line, everything that the adversary, this corrupt party, sees is total random garbage. Okay, and this is actually, you'd have to think about it some, but this is even if people are acting maliciously and so forth, this is some sort of secure evaluation of some sort of empty function. So if you don't send these last messages, the adversary has learned nothing. Okay, another observation. In the final round of this protocol, so what did we do? Everybody just sent out their shares of one of these replicated secret sharing values. This is robust in the following sense. Okay, so say that y was the value that we had here. And so given one party, I guess now I have it, the corrupt guy, you expect to get so what is sort of the missing value here? You're getting 2 copies of the same thing from the other 2 parties. Okay, so this actually makes more sense if I'm looking in the other direction. So some honest guy gets shares from the other 2 people, and there's one share that he doesn't know. This is really what's giving him the information of the final output. And the point is that he's expecting exactly the same value from the 2 parties. This is important because if, for example, the adversary decided to change his share to some garbage, this would be identifiable. Okay, so here are robust shares of the output in the final round. And the final thing is that if it's the case that these really are sort of correct additive shares of 0 that are generated here, and so remember that there was some sort of operation for each multiplication gate. You were supposed to you had some shares from previous. You were supposed to multiply them in a particular fashion, add them up, and then send something out. If you performed that step correctly, if each and every one of those steps was performed correctly, then you, sort of trickling through the circuit, you have the property that the thing you compute, these shares at the very end, really is the circuit evaluated on the inputs. Okay, and in fact, this piece here is exactly, so sort of the combination of these 2 is how you prove security, exactly how you prove security of this protocol in the passive adversary model. So here this allows you to say that nothing's leaked, and then at the very end, so in the very end, you're guaranteed that this really is correct so you don't have to do anything here. This holds already because you're assuming the guy is acting semi-honestly, that he's following the protocol. Then you can kind of simulate the final round message given here. Okay, so these things are going to be the natural properties that our protocol needs, that our compiler needs, okay? So if you have any protocol, and in fact, this is actually a very common structure. A lot of protocols, if you kind of look around in literature, do have this sort of form. So if you have this package of properties, then our compiler will apply to you, okay? Okay, so maybe to try to kind of give you a little bit of intuition, I'm actually not going to dive into very much detail, but again, so why is this going to be useful? Actually, let me go for it. Okay, so here is going to be the compiler, and in fact, maybe you've even started thinking about this at this point. So remember, this is the structure. Forget about the protocol itself. I'm assuming it's some natural protocol that had the properties from the previous slide. That means that there's some initial part, pi prime, without the final message, and this final message, okay? What we're going to do, you ready for this? This is the most elaborate animation I'm going to have here. Right there, okay, squeezing in there. The new protocol will run this without a change, okay, identically this pi prime. Okay, but before sending the final message, the parties are each going to prove to each other, okay, in zero knowledge, that they really did follow the protocol up to here, that each step that they made, each message, followed what they were supposed to do. Okay, and to be honest, this is not a new framework. This is, basically what you would expect. And in fact, there are other protocols that have similar approach here. But sort of the power, or maybe what's new here in this work, is that we give away this fully linear PCP and proofs on distributed data directly give you a way of doing this, and in fact, with small communication. Okay, so, so first of all, if any party is rejected here, you abort, and otherwise, you do exchange the final message. Okay, so zooming in a little bit more on this box here, what really is going to be happening. So why is it this proofs on distributed data is exactly in line with this? So what I'm trying to prove, okay, so think of, I'm one of the three parties here. I'm trying to prove that everything I did up above was exactly what I was supposed to do. Okay, so the statement is just think about the appending every single message that I sent out or received in during the protocol. Okay, so neither of you two has this statement in full. Okay, but each of you, kind of by definition, has a part of the statement, such that if you bring them together, you would have exactly all the messages that were sent in or out during the protocol. Okay, and what I need to assert is that this collection of messages satisfies the particular degree 2 relation. Bingo, this is exactly what we have. And so here this is an example of one of the simple relations. We have these fully linear PCPs with sublinear size proofs. So that means that the communication that we're going to have here, in order to prove to you guys, I basically have to additively sequencer this proof, send it out, but this is going to be sublinear in the size of the circuit that we were computing. Okay, just kind of one small note here. The soundness, if you just apply this directly, the soundness error will be something like 1 over the field size or the ring size that you're working with in the circuit. But as I mentioned before, that's okay because we can actually embed directly. So all of the pi prime, the protocol itself is done, say, over the Boolean or whatever. Now, only for the part of the proof, we'll embed this into some sort of bigger structure so that we can get small soundness error. Okay, and it's still going to be sublinear in the circuit size. Okay, so just kind of putting these pieces together. Again, our new protocol, you run the original protocol except for the final message. Each of the parties will prove to the other two in this distributed manner that they performed their steps correctly. And then if so, then you're sort of safe to exchange the final message. Okay. This is already a wrap-up slide. So the only goal of this slide is to get you intrigued by the more than 3-party case, to put a couple challenges. So the first challenge, and this came up a lot in questions in Henry's part, So up until now, in the three-party case, you have this very convenient setting, 3 parties, 1 corruption, where either the prover is malicious or one of the verifiers is malicious. Okay? But if you have more parties, you can have, and in particular more corruptions, you can have the case, for example, where malicious prover and verifier could be colluding with each other. And here, it really actually opens up a lot of interesting questions. Even, for example, defining soundness becomes a little bit tricky. And in order to achieve it, this requires that whatever the statement is somehow robustly encoded across the different verifiers. Okay, so that's great. But then, because of this robustness requirement, it turns out, so this transformation becomes more tricky because it's no longer the case. So before it was the case that my statement X was just the messages going in and out here. But at this point, this is not a robust statement. It only becomes robust in this case if you also include messages going between the other people. So it's no longer the case that the prover actually even knows the full statement he has to prove something about. Okay, so here we end up using a different structure for the compiler. I'm not going to tell you about it, but feel free to ask me about it afterward. Okay, so just to sum things up, fully linear PCPs have a lot of really interesting applications on proving on statements where you don't have the statement in hand, but you somehow have, say, linear access to it. Okay, and as one example of this, we have a new compiler going from passive to active security in MPC. So I'm already massively over time. I think I won't spend time about future directions. Let me just very briefly, so here, clearly for multiple parties, dishonest majority is a whole different can of worms. And one last mention, so the active security notion that's achieved in the previous transformations is security with abort. So for example, if somebody's rejected, you abort. You could hope to try to get in this setting full security together with output, guaranteed output delivery. That's what I mean by full security. So we do, in the specific case of 3 parties, we have a follow-up work together. So this is together with Yuval and Ariel Nof that does achieve this. But the end party case seems a lot more tricky than 3 parties. So there's interesting places to go.
Since we're massively over time, thank the